So in our dealings with conservation of energy, we've restricted ourselves to looking at isolated systems and that there's going to be no energy loss in that system. Now, realistically in life, there is going to be energy transferred out of your system. That's just going to be how it is. Like friction is absolutely going to do something like this. Now, we can still actually do that. We talked about the Work-Energy Theorem a little bit earlier. We talked about how the work done on an object is actually equal to its change in energy. Well, we can use that to our advantage in the case of a non-isolated system. So that change in energy is just going to equal to this external work that's occurring. So if I have friction that's doing work, we would say that that's external work. And then we'd say that that work due to that friction is going to equal to the change in mechanical energy of that system. So we've been using this idea already for conservation of energy. We would just say that the external work is zero in an isolated system. So we get delta E equals zero. And then that's where we'd get like delta EK equals negative delta EP or vice versa. So we're actually going to use the Work-Energy Theorem to look at some non-isolated systems. In terms of sign conventions, it's two things. If energy is being withdrawn from the system, like with friction, we're going to put in the external work as less than zero, so it's going to be negative. If it happens to be added to a system, like through a motor, we're just going to say the external work is greater than zero. So we just have a couple graphs here just to show like the decrease in mechanical energy as a function of time or the increase in mechanical energy. So here we're having energy being transferred out of the system, and you'll just see that no matter where we're looking, EP plus EK is always going to equal to EM. We always still, that rule of EM equals EP plus EK still holds in a non-isolated system. All that's changing in a non-isolated system is that EM is not constant. Whereas if we have an increase in mechanical energy, there's energy being transferred into the system, and then you're going to see that mechanical energy transferred in as a function of time. Now, non-isolated systems, people might start to get a little fearful and think like, oh man, this is probably really hard. It's actually not as bad as you think. We're going to look at a couple examples in a non-isolated system, and you'll see we can actually ignore quite a bit. So let's look at this. We have a 250 kilogram ball is atop a ramp that is 5 meters above the ground. So once the ball reaches the bottom of the ramp, it encounters a rough surface with a coefficient of friction of 0.150. Determine the distance that the ball travels along the rough patch before it comes to a complete stop. So what's going to happen, and we're going to assume the ball doesn't roll, so we're just going to assume it translates from here to here. Not realistic, but again, we're simplifying it to our needs in Physics 20. So ball's going to come down to the bottom here, and then it's going to hit a rough patch, and it's going to move along until it gets to this point here. What we'd like to find out is how far does that ball have to travel on this rough surface before it comes to stop. Now, there are multiple ways to do this. What I want to do is I want to look at it through the Work-Energy Theorem. So we know that the work is equal to the change in energy. Now, for us, because we expect the work done here, we expect that to be negative because we're going to have friction involved. So we do expect the external work to be less than zero. Now, we also have a definition for work. So our definition for work is just going to be the force of friction multiplied by the distance here. And then I'm actually going to put my negative, or actually I'll explain that in a moment. So I have my force of friction times this distance, and then the change in kinetic energy, or change in energy is just going to be my change in kinetic energy plus my change in potential. Now, I can pick the 2 points I'd like to analyze. So I'm going to call this my starting point A, where we start, and then B is going to be my ending point there. You're free to choose the 2 points of interest. But since we're finding the distance we want this thing to roll or to move before it comes to a stop, we're probably going to need to include that point at the very end. So for me, let's put this FFD equals, so my delta EK, I'm going to have this half MVB squared minus half MVA squared, and then I'm going to have this plus mg delta H. I have no mention of springs, elastics, so we don't have to worry about elastic potential energy. This is also why we try to tell you that a choice of reference helps a lot. At the start, this ball is at rest. When we get to the end here, it's also going to be at rest. What that means is we get to get rid of our terms for kinetic energy because it's not moving at the end of its journey and it's not moving to start with. So those terms are gone already. that helps us quite a bit. What we're left with is the force of friction times this distance. This is just going to be mg delta h. We want to find that distance. So we know that the distance is just going to be mg delta h over this force of friction. Now, with that said, let's see what we got going on here. We know mass, we know g, we know the change in height. We'd like to find the force of friction. At the moment, we're a little bit hooped, but this is where our free body diagram and all our tips and tricks with dynamics come in. Friction's only going to apply on the rough patch here. So once this ball is on the rough patch here, we can draw a free body diagram for that. So we certainly are going to have this force of friction trying to bring it to a stop. We also have force of gravity, and we also have a normal force. Now this object having balanced forces in the y direction means that the magnitudes of these are going to be the same. So on the friction surface, so we know in the y direction, and I guess I should assign some directions here. I'm going to call up positive, and I'm also going to call this direction positive to make our force of friction negative. In the y direction, we know that Fn plus Fg is going to be 0. And we know that, because we know that there's no movement in the y direction. So we're going to have this 0 equals Fn plus Fg. Now, what we do know is that Fn is going to be the negative of Fg, or Fn is going to be negative mg. Now, we can live with that. We also know by definition the force of friction. We know the magnitude of the force of friction is just going to be mu times the absolute value of Fn. And this is where we have to be a little bit careful here, but I'll address that in a moment. Now, Ff, the magnitude of that is going to be mu, and then we have this negative mg here. Now, we might be a little bit worried, as we should, so I'm going to take into account those magnitude bars there. We haven't always been good with that. So what that is telling me is that the magnitude of my force of friction, it's just going to be mu mg. We're not actually worried about directions. But when I plug it into here, I also have to realize that the force of friction is going to be negative. It has to be according to our free body diagram. So I have to find a way to tack on a negative in there somewhere. So what I'm just going to do is I'm just going to put this mg delta h, and then we're just going to say this is minus mu mg. So the advantage for this is that all our considerations for m and g are gone. So what we're left with is that this distance is the change in height over the negative of the coefficient of friction. Now we might be worried with that negative here, but keep in mind this height, we're dropping down 5 meters, and our height, it's always going to be the height at our final point minus the height at our initial point. So we could say that this is a height of 0, that's a height of 5. So we're dropping down 5 meters, so we're going to actually say the change in height is negative 5 meters, and then we're going to divide that by this negative 0.150. So what this is going to do is this is going to tell us that for this object here, in order for it to come to a stop, it has to travel about 33.3 meters on that friction strip. Now, as I mentioned, this is one way to tackle the problem. There's actually quite a few ways that we could look at this, but I've just opted to look at it through analyzing conservation of energy and the Work-Energy Theorem. But you're free to do it whatever way you like. This is a particularly hard example because, again, we have to be really careful with our signs here and that whole magnitude thing. But if you find you're getting a negative here, probably just means you can lop it off. But try not to rely on that too much. Right, let's look at one more example of this. This is also, it looks a lot harder than it is. So we have this 0.50 kilogram ball. It's starting at position A, which happens to be 7.5 meters above the ground. So it's pushed down an incline. So by us saying it's pushed down, this is telling us that it has an initial velocity and it's not 0. So friction is going to produce 10.7 joules of heat energy, and the ball is going to leave the incline at position B, and it's going to reach a height of 13 meters above the ground. What we'd like to do is we would like to determine the initial speed at position A. So we have quite a bit going on here. Now, let's see. Let's look at this diagram. We're interested in position A. That's absolutely critical because we want to find that initial speed V0. We know it's height above the ground. At B, we don't know how fast it's going there, so that's not particularly helpful. But we know that this ball is going to reach maximum height, which tells us that its speed is going to be 0 at this point. It's going vertically only, so we don't have to worry about any like X component or Y component. So I'm going to call this position where we have the maximum height, I'm going to call that position C. So for our equation for conservation of energy through the work-energy theorem, we know that the work is just going to be the change in energy, or the work is going to be delta EK plus delta EP. Now let's have a look at this again. So the two positions I'm going to be examining is this position at the maximum height, that's what I'm calling C, or this would be like my final position. My initial position at A, we can also determine the kinetic energy here. So we're going to have this half mvc squared minus half mva squared. So this gives me my kinetic energy at this point. Then I have to subtract off my initial kinetic energy at this point. And then potential energy, we're just going to have mg delta h. Now, at maximum height, we know that there's no kinetic energy because there's no speed at this point. So this term is going to go away. We don't have to worry about it. So what I'm left with here is I'm left with work equals negative 1/2 mva squared plus mg delta h. What I would like to do is I would like to find VA. Now, I would like to also have it as a positive. I don't want this negative out front. So what I'm going to do is I'm going to move this to the other side. So I'm going to get this W plus half mva squared. This is going to be mg delta h. And then we're going to take this work term and put it on the other side. So we're going to get half mva squared equals mg delta h minus the work. Now, at this point, you can simplify how you would. I'll plug in some numbers here first. So I'll find out what this kinetic energy is at the initial point. So the kinetic energy at the initial point, A, we have this mass of 0.50 kilograms. We have this 9.81 meters per second squared. Change in height. Now, change in height has to deal with the difference in height from where I started to where I ended. So I started 7.5 meters above the ground, and I ended 13 meters above the ground. What I'm interested in delta H, which is actually going to be this piece right here. This is going to be my delta H. So that's going to be my 13 meters minus my 7.5 meters. So at the end of this journey, relative from where it started to where it ended, the ball had a vertical height change of positive 5.5 meters. So that's what we're going to put in here for delta H. So we're going to put in that positive 5.5 meters. And then I have to subtract off my work. We have to be careful though. We're told friction produces 10.7 joules of heat energy, but friction is going to rob the system of energy. We have to put this in as negative 10.7 because this is negative work. So negative work for friction. Really important there. So let's calculate the kinetic energy at position A. So the kinetic energy at position A, so we get that 9.81 times 5.5, and then we have this piece here. So we're going to get about 37.6775 joules. So that's my kinetic energy at A, or half mva squared. All right. And some of you might say, do I have to do this? Could I just rearrange this for VA and solve? Absolutely. I'd never stop you from doing that. Sometimes we just want to show different ways of doing this. So I know that my kinetic energy at A is going to be this 37.6775 joules. So last thing, VA is going to be twice this 37.6775 joules. And then we're going to divide that by this mass of 0.50 kilograms. So last thing, let's calculate that. So what we're going to get here for significant digits, we'll get about 12 meters per second. So what this is saying is that based on all of the information that I've been provided in the question, when this thing started out, it wasn't just let go to go down the incline. This person gave it a push of 12 meters per second down the incline. So down here they gave it a nice little push of 12 meters per second. Friction robbed it of about 10.7 joules of energy, and then this thing got to and then based on all that happening, this got to a maximum height of 13 meters above the ground. So the work-energy theorem is meant to take some of the bite out of non-isolated systems. We don't focus a lot on this, but I just want to show this to you because some of you will probably do physics at the post-secondary level, and you're absolutely going to deal a lot with non-isolated systems there.